So this is going to be lesson on 1.2, Newton's first law of motion. So Juno begins by saying a woman is applying a force upwards on the bag handle. So let's take a look at this GIF, right? The question says, what force is pulling down on the bag handle? So this man is giving this woman, she's holding two bags connected through a handle. You can't quite see it, but that handle is connecting both of those bags. The man proceeds to put a pie on top of her hands, and proceeds to cut it, and the pie goes to her face. Right, and the question here is, what force is pulling down on the bag handle? And if you pay attention to lesson 1.1, well, there's only really one force pulling down the bag handle, and it's the force due to gravity on the bag. So the force due to gravity is pulling on the bags here. And so Newton's first law. Now we will go into explaining Newton's first law. You can just read it from here. Newton's first law states that objects experience a change in motion only when unbalanced forces act on that object. But there's a lot of vocabulary here, right? What is an unbalanced force and what are balanced forces? Now, to be balanced, right? So first off, to be balanced, your net force must be zero. So let's go back to the simulation here, right? So if we have one child on this side, and well, how are we going to balance this force? How are we going to balance these forces? Well, we're going to put another child on the other side. Right, and let's say I have this right here. Well, how would I balance my forces here? How would I balance my forces? How would I get my net force to be zero? Well, I would have to just add another person on the other side. And now my forces here are balanced. My forces here are balanced now. So again, the definition of balanced forces is that your net force here is zero. That is the definition of balanced forces. Balanced forces. Now, unbalanced forces are when your net force is not zero. Right? For example, how would I make my forces unbalanced here? Well, I could just take away one person and now my forces are unbalanced. There's less force on one side and more force on the other side. My forces are unbalanced. And so my net force here is not equal to zero when my forces are unbalanced. And it's only when your forces are unbalanced that your motion starts to change. Right? As you can see in the simulation right here, well, when we had an unbalanced force, when we had more force on one side, well, the object started moving to the right. On the other hand, if we have equal forces on both sides, if we have balanced forces, well, nothing's going to happen, right? There's no change in motion here. Nothing's going to change, right? There's no change in motion. So let's analyze this question on this slide right here. And the question says, what force disappears here and causes the force to be unbalanced? Take a look at this, right? So let's take a look at this person. And so before the situation, right? So let's say the bags are connected before he cuts the bag. The woman is applying a force upward. So the woman is applying a force up on the bags, and there's a force due to gravity acting downward, pulling on the bags. And this is before the man cuts the bags. But after he cuts the bags, well, what force disappears? What force disappears and is the only force left? She's still applying a force up on the bags, right? The bag handle, rather. But what just suddenly disappeared, what force disappeared was that when he cut the bags, well, then my force due to gravity disappeared. There was no longer a force due to gravity acting on her hands from the bags. And now that my forces here are unbalanced, right? Before my forces were balanced, my F net here was 0. Now that my forces are unbalanced, she's gonna move that pi on her hands upwards, right? So there's an unbalanced force here, right? So what force disappears? Well, my force due to gravity disappears here, and all I'm left with is my force, applied force from her hands. And so this question says, well, draw the free body diagram of this picture, or rather of this GIF, right? So you can see in this GIF, you can see in this GIF, is that you have a ball hitting the dirt, right? And the racket goes downward. Now, if we want to take a look at this, right? If I want to draw a free body diagram of all my forces acting on the dirt, let me just use a different color. Let's see, red doesn't work too well. Maybe blue. Blue should be fine, right? Right, if I want to draw all the forces acting on my dirt before the ball hits the dirt, rather hits the racket, well, there's a force due to gravity acting down on the dirt, and there's a normal force acting upwards on the dirt, right, from the racket. The racket's holding the dirt up, so there's a normal force acting on the dirt from the racket. And this is the free body diagram of our racket, of all the forces acting on the dirt before the ball hits the racket. And well, what does the free body diagram look like? And what does the free body diagram look like after the ball hits the racket? And so after the ball hits the racket, well, now there's only a force due to gravity acting down on the dirt, and there is no longer a normal force. And so my force due to gravity is my unbalanced force. Nothing is balancing it, right? Nothing is holding this earth up, which means that this dirt is now free to fall after the ball hits the racket. And the dirt starts falling because there is unbalanced force acting on that dirt. This question, you see some guy jumping out of a train, right? And what's the unbalanced force acting on the guy's shoe as he jumps out of the train? The unbalanced force is the force due to friction. The force due to friction from the floor connects with his shoe, slows him down so he doesn't keep going. A really important part of Newton's first law is the idea of inertia. Right? And inertia is really just a tendency of any object to resist changes in motion. And the more mass you have, the more inertia you have. Right? So more mass you have, let's take for example this haystack. Right? This haystack has a lot of mass. Doesn't really want to change its motion, right? Because it has a lot of mass, a lot of inertia. So this haystack is going to keep going. This human does not have enough mass to stop the haystack, right? He doesn't have enough inertia. And so the haystack just completely ignores him and keeps going. And how fast something is going has no relation at all to inertia. Velocity does not matter. It doesn't matter how fast you're going. Inertia is only proportional to your mass. Again, inertia, in other words, objects that will want to keep moving will want to keep moving, or rather, objects that are moving will want to keep moving, and objects at rest will want to stay at rest. Case in point, the top two GIFs. Let's take a look at the top left one. The guy on the skateboard. His skateboard gets caught on the hose, and the man on top of it Well, he continues going. Objects that are moving will want to keep moving. Same thing with the soda bottle, soda can, right? The car is moving, the soda can is moving. The car stops, but the soda can wants to keep moving and so falls over. The baby is at rest on the bottom. The dog moves. Well, the baby wants to stay at rest. Let's do some practice here. Which object has the greatest inertia? Again, mass is proportional to inertia, and velocity has no effect on inertia. So D has the greatest mass. Object D has the greatest mass, meaning it has the greatest inertia. A 0.5 kilogram cart is rolling at a speed of 0.4 meters per second. If the speed of the cart is doubled, the inertia of the cart is what? Again, velocity has no effect on inertia, only mass does, so your inertia here is unchanged. This question is asking you which object has the greatest inertia. Again, mass is proportional to inertia, so D at 20 kg mass has the most mass, thus the most inertia.